Suppose this is a sphere of this center. So if a portion of this sphere is taken out, so this portion, if we cut the back, then the inner portion is concave. So this center of the sphere, where this concave mirror is gotten from, is called the center of curvature, C. Now let's draw a straight line, horizontal line, through the center of curvature. This line itself is called the principal axis. And this point where the principal axis cuts this aperture, this part of this sphere, this aperture, so here we call it the pole. Aperture, principal axis, center of curvature, pole. Now halfway between the center of curvature and the pole, halfway we call it F. We call it the principal focus. Why is it called principal focus? Whenever we have rays that are parallel and close to the principal axis, after reflection, they will meet at the center of curvature. Sorry, at the principal focus. Let's look at this. Here we have rays that are parallel to the principal axis. We notice that after reflection, because they cannot pass through, they all meet at the what? Principal focus. So these are the reflected rays. And they do what? They meet at the principal focus F. Now the distance between the center of curvature and the pole is called the radius of curvature, R. The distance between the center of curvature and the principal focus is called focal length, F. And since this F is midpoint between C and P, it implies that from here is also F. So it means the principal focus of the focal length is what? Radius of curvature over 2. Let's write out all those parameters. So center of curvature is the center of the sphere from which the aperture is removed. What's the aperture itself? The length of the mirror from this point to this point is called the aperture. The pole is the center of the aperture. The principal axis is an horizontal line that passes through the center of curvature and the pole. What about the principal focus? The most important part, which they normally ask in exam. So for principal focus, it depends. For example, this mirror is a concave mirror because it's bent inward. So it's a concave mirror. But something about concave mirror is that when parallel rays hit them, they converge at the principal focus. So that's why they're also called what? Converging mirrors. So note, concave mirrors are also known as what? Converging mirrors. Why? They converge after what? Reflection. So what is principal focus? Right. This one is most important. So principal focus is a point on the principal axis. Principal focus is a point on the principal axis where parallel rays converge after reflection. They converge after reflection. That is for what? For converging mirror. Meaning for a concave mirror. We also have the opposite diverging mirror. We are coming back to that. But for example, let's move on. Radius of curvature is the distance between the center of curvature and the pole. While focal length is the distance between what? Center of curvature and the what? Focal length. And the principal focus rather. The distance between C and F is called focal length, or between F and P is what? Focal length. And this is how they relate. Now let's do something different. Let's take a part of this sphere. So this is the center. But instead of coating the external part, let's coat the inner part. If we cut the inner part, the external part becomes the deflected surface. So this external part is what? It's convex. So this is a convex mirror. See this center. Let's clean this other side. So this is a convex mirror and it's also called a diverging mirror. Why is it diverging mirror? We'll see that now. So let's draw this center of curvature C. Let's say this is the pole P. This is the aperture from this point to this point. Now let's draw the principal axis to join P and C. Then the principal focus will lie in between. So this is from here to the radius of curvature. Now let's suppose we have parallel rays coming towards this mirror. So unlike this one that after reflection they met at the principal focus. First here, the principal focus is within the mirror. Here, the principal focus is outside the mirror. So that is why in this case the focal length, which is between the pole and this, is going to take to what minus f, because it's at the back of the mirror. So what happened here is at the end of the day after reflection, the rays will scatter. Something like this. So this will be the reflected rays. They scatter, meaning they diverge. So, but if you trace them backward, if you trace all the rays backward, you will see that the divergence started from the principal focus. But note, we use only rays. So here we can still say principal focus is a point on the principal axis where rays diverge after reflection, but in this case converge after reflection. So somebody can ask you, define principal focus as applied to a concave mirror. In that case, you say what is a point on the principal axis where parallel rays converge after reflection. If it's for convex, where they what diverge after what reflection. And that's why convex mirrors are called diverging mirrors, because rays scatter after what reflection. Note, unlike plane mirror, the characteristics of image is always constant. You always get virtual image, upright, lateral inverted, same size, same distance, But for especially concave mirror, if we place our object at infinity, a point very far from the mirror, what we'll get will be different from if that object is close to the center of curvature. If the object is placed on the center of curvature, we'll get different image. If it's between C and F, different image. On F, different image. Between F and P, we get different image. So next is to talk about the characteristics of images formed by a concave mirror, characteristics of image formed by a convex mirror. But before that, note the following about what curved mirrors. Please note this, the corollary. First, if we have any ray parallel to the principal axis, after reflection, it must pass through the principal focus, like this. Secondly, any ray that passes through the principal focus, after reflection, it must be parallel to the principal axis. If it passes through F, it will reflect a parallel. If it enters parallel to the principal axis, it will pass through F. Then, lastly, let's say this is C. So any ray that passes through the center of curvature, like this, it will be reflected or it will deviate 180 degrees. Any ray through C will deviate backward through C also. If it enters this way, it will reflect backward. So know these 3 points. So these 3 things will be important in order for us to get the characteristics of images formed by what? Curved mirror. Let's go into that now. Don't forget this. Any ray that passes through the principal focus will be reflected parallel to the principal axis. Any ray that passes through the principal focus, any ray parallel to the principal axis will be reflected through the principal focus. Any ray that passes through the principal focus will be reflected parallel to the principal axis. Any ray that passes through the center of curvature will be deviated 180 degrees, meaning it's going to be reflected through the center of curvature. Draw this 3 diagram out and write the points below each or above. Let's take them one by one. So this same mirror, when the object is placed behind C, what happens? On C, what happens? Between C and F, what happens? On F, what happens? Between F and P, what happens? So let's erect object there. So what happens? As the object moves closer to the mirror, what happens? So remember the 3 points I gave you the other time before we started this. First, we take a ray parallel to principal axis, then it pass through what? Principal focus after reflection. Then any ray that pass through F will also be related parallel to the principal axis. Let's do that for the first one. Rays that are parallel to the principal axis pass through F after reflection. Next, ray that pass through F, when they hit this, the words be parallel to the principal axis. Reflect. So where the 2 rays met, that is where the image is going to be formed. Now, what kind of image will we form here? Note, we took the rays from the head, so this will be the head. So it is formed below the principal axis. So what happens? if you have to measure the length of this or the height of this and it, you know that this one is smaller. So it is smaller. First note, if the image is from, this is the front of the mirror, this is the back. If the image is from at the front, then the image is real. So the image is real. Then it is formed below the center of below the principal axis, so it is inverted. And the size gets smaller, so it is not magnified, but it is what? Diminished. Diminished. And it is formed between what? C and F. That's the position between C and F. So we can summarize this as what? RID. Real, inverted, and diminished. And the position is between C and F. Meaning, if an object is placed behind the center of curvature, the image will form between the center of curvature and the principal focus, and it will be real, inverted, and diminished. So let's do the same thing for the next one. What if it is placed on C? So take ray through this and pass through F. Second will pass through F, then it will reflect parallel to the principal axis. Go this way, and what happens? They met here. So this is where the image is going to be formed. So the image is also real, it is inverted, but when you check the size from here to here, then from here to here, they are the same. So same size. Same size. Then it is formed between, it was formed on what? On C. So if the object is placed on C, the image will be placed on C. And the characteristics, real, inverted, and same size. So for this one that is diminished, it means magnification is less than 1. For this case, magnification equals to what? 1, same size. Now let's move it further between C and F and see what will happen in this case. Same way, we take a radio parallel to principal axis. Then after reflection, it will pass through F. Then secondly, we take ray through F. After reflection, it will pass through what? It will be parallel to the principal axis. Incident ray, reflected ray, incident ray, reflected ray. What happens? They met here. So, if you check, this one is apparently longer than this. This is longer than this. Front of the mirror, it is real. Below principal axis, it is inverted. Now it's bigger, it is magnified. So magnified. Then where is it formed? Behind C. It is formed behind C. And what happened to our M? Our M here is greater than 1. It's bigger. It's magnified. So that's rim. So we first have what? Read, wrist, rim. What happened next? Now the object is now at F. Same way, rays parallel to the principal axis will do what? Will be reflected through the principal focus F. But since this one is standing on F, ray cannot pass through F. So we are going to use the second corollary. So ray that pass through what? C. Rays through C. Let's bring this one up this way. So rays through C will move, will be deviated by 180 degrees. So this is the mirror here. So if the ray pass through, C. After reflection, it will move backward towards C. It will move backward towards C. And what do you notice? Unlike all the previous cases, reflected ray met here, they met here. This one they met here, but for this one they are parallel. If they are parallel, it means they will never meet. So if they do not meet, what happens? It means the image will never be formed. The image will only be formed when the rays meet at infinity. So meaning no image is going to be formed. So because the image is going to be formed at infinity. So meaning if the object is placed at the principal focus, the image will be formed at infinity. Now let's now bring it closer. Let's place the object between the principal focus and the pole and see what we are going to get in this case. So same way here, rays parallel to the principal axis will We pass through what? Principal focus after reflection. Now, we cannot take ray through F because this one is already beyond F. So now let's not use the third one through C. So let's extend this. Let's draw it wider. Now let's take ray through C. So any ray that passes through C, what reflected through the same path. What you notice, unlike this one, they are parallel. They didn't meet because they are parallel. These two will not meet because they are diverging away. But when rays are diverging away, if we go backward, it means the divergence started from a point. So when you trace one backward, and also trace one backward, they will meet at a point. So that's where they met. So whenever the two reflected rays met, that is where the image will be formed. So now the image is going to form here. First, it is formed at the back, unlike the previous ones. Since it is formed at the back, it is virtual. Now it is standing upright, unlike the others that are inverted, so it is erect. What one is now bigger, it is magnified. Magnified. So what's the acronym? VEM. Virtual, erect, and magnified. Where is it formed? Behind the mirror. Behind the mirror. And our n is greater than 1. It is magnified. Let's label each case. First one is when the object is placed behind C, center of curvature. The next one is when object is placed on C. Object placed on C. Next, object placed between C and F. Next, object placed on F. Then last, object placed between F and P. Now let's summarize this. This means when an object is placed in front of a converging or a concave mirror, the imaging form are always real and inverted. Real inverted, real inverted, real inverted. Except when the object is placed between F and P, principal focus and pole, where it is virtual and erect and always magnified. We only get virtual and erect when the object is placed between F and P. Every other case apart from this infinity, it is real and inverted. And as the object is moving closer to the mirror, what happens? The image gets bigger. Initially, it was diminished, same size, magnified. Read, ris, read, infinity, VEM. You can memorize that. We have read, we have ris, we have rim, we have infinity, we have what? VEM. So these are the characteristics of the image formed by the mirror. And as the object moves close to the mirror, the image moves further away. Look at it, see the object, see the image. Object, image. So as you can see the first image, you can see the blue are moving closer, and the red are moving what? Further away. So when this one is formed as infinity, the next is for it to what? To come to the back. To be virtual. To become virtual. Now note, because of this last characteristics, write this, it's very important, right? After this, write this down. Concave mirror are used as shaving mirror. They are used as shaving mirror. Why? Because they give an erect, being virtual is not really important here. They form erect and magnified image. So when you place your face very close to the mirror, it means your face is between F and P. You see the image of your face is going to be erect and magnified. So they are used as what? Shaving mirror. Then we have a special case of converging mirror, concave mirror. But these mirrors are not formed from a sphere. You know, all these mirrors, they are formed from a sphere. I draw a circle first. What if you have oval and we remove an aperture from it? In that case, you are going to get what we call a parabolic mirror. Let's look into it. It's very brief. Then after that, move to convex mirror. So to see what are the characteristics of images formed by a convex mirror depend on the position of the object. So quick, let's talk about parabolic mirror. Ensure you draw everything here one by one. Draw it yourself to understand it. And know these characteristics because they are very important. Now look at this diagram. Suppose it's center, but we don't call it center in this case. Let us draw the principal axis. So this is like the center of curvature. So let's take out a portion, and we should quote this back. So this becomes a parabolic mirror. pole, principal focus, F. Now recall, any ray that passes through F will be reflected parallel to the principal axis. So this parabolic mirror, they have many uses. They are used to produce what we call parallel beam of light of high intensity. So if you put a light source here that gives us a diverging light source. So the light source are moving from the principal focus. Now the question is, what will happen? All these rays will do what? Will be reflected parallel to the principal axis. Then we have something like this. Parallel beams. And these are not just parallel beams, but beams with constant intensity. So they have constant intensity and they have high intensity. If we are to use normal concave mirror, I will place the source at, let's say, F. Yes, we are also not going to get parallel beams, but they won't have constant intensity. Some places more intense than the others. Those that are very close will be more intense than the others. Some parts will be bright, some parts will, so it will scatter a bit, although they are still parallel. So this one has what? Constant intensity. This one doesn't have a constant intensity. So now, these parabolic mirrors, they are used in many ways. First one, they are used in car headlamps. So when you check the car headlamps, there is a mirror inside. That mirror is not just a concave mirror, but it's a parabolic mirror. So I'm very close to that mirror, you see a small light bulb. Yeah, light source. So when this come on, what happens? Light will come from the principal focus and touch the parabolic mirror. I have what? Parallel beams of what? Constant intensity. So they are used in car headlamps. They are also used in searchlight. They are used in searchlight or searchlight. They are also used as spotlights in concert hall. So in auditorium, when we want only the presenter to be seen, then the spotlight to be incidented on the person. They are also used in the hospital during surgery, so as surgical lights, mainly because of their what? Constant intensity. In case you're asked, why are parabolic mirror used instead of what? Concave mirror in car headlamps? The answer is it's because parabolic mirror gives parallel beams of constant intensity. Now let's move to convex mirror. Let's clean this concave and write convex, and let's clean converging and write diverging, because concave is converging while convex is what? Diverging. For mirrors, not lenses. We are still coming to lenses later under refraction. Now we are done with converging, meaning concave mirror. Let's talk about convex mirror. But the good news is, unlike concave mirror, for convex mirror, no matter where the object is placed, the characteristics of the image form is always what? The same, and which is what? VED, virtual, erect, and diminished. Let's show it. Principal focus, center of curvature. Let's place the objects here. Ray diagrams. Any ray parallel to the principal axis will pass through F after reflection. So because this is a diverging lens, or mirror rather, so when the light touches, it reflects, it's scattered. So next, let's trace backward to show that it's passed through F. Yes. Next, any ray through the center of curvature will be reflected along the path. So the first one, parallel ray passes through F and diverge after reflection. Secondly, any ray that passes through C or that passes towards C will be reflected along the path backward. So, but if you trace it, the met here, so that is where the image is going to be formed. So this is the front, this is the back. Because the image is formed at the back, we say it is virtual. It is standing upright, it is erect. Now we have a draft here, so it gets smaller. diminish. So that's what? Ved. So no matter where the object is placed, the image is always what? Ved. Now, advantages of convex lens over concave lens. For concave lens, we cannot actually predict where the image will be, whether the image will be erect or diminished. So we have reed, ris, rim, infinity, and ven. So sometimes the image will be inverted, sometimes it will be erect, and the size varies. You cannot actually see for certain what will happen. Even at a point in time, the image of the object disappears because it will never be formed. It can only form at infinity. So, but for a convex mirror, it is always what? Erect and diminished. So, because it's always erect, we use it as what? Driving mirror. So, in case you ask, why are convex mirrors used as driving mirror? Right, it's very important. Convex mirrors or diverging mirrors are used as driving mirror because one, they always give us erect image. If you use concave mirror as driving mirror, what happens? It means at a point in time when you look backward, some of the cars behind will be inverted. The wheels will be up and the driver will face down. So that will cause commotion. So it will be erect. And most importantly, because they form diminished image. For example, let's go to the surface of the mirror. If you have an object, let's say these are cars. So these cars will appear smaller here. So if they appear smaller, there will be enough space for more cars to be reviewed or to be shown through it. So they have what called a wide field of view. They have a wide field of view. Meaning, on the mirror, multiple images, plenty images can be shown there. So they have what? Wide field of view. Why? Because they make all the objects to be diminished. And the objects are always erect. But there is a little disadvantage. So when you look at objects through the mirror, it will be as though the objects are far. Suppose this is the object and this is the mirror. So when you observe this object through the mirror, it will be as though this object is somewhere here. But in real life, the object is somewhere here. So meaning objects are actually farther to the mirror than they appear. So they are closer rather. They are closer than they appear. They are close, but you see them as though they are very far. So it means the objects are actually closer than they appear. So that's why they are going to write on the driving mirror that objects are closer than they appear. Meaning the image you are seeing is farther than what is there in reality. So objects are closer than they appear. So if you are driving, you have to work on your reflex to know that what you are seeing is not real. What you are seeing is closer. Just like your examination, they are closer than they seem. So on the application, very brief, concave mirror are used as shaving mirror because they give us erect and magnified. For convex, they always got erect, but they will not magnify, they will diminish the image. So they are not good as shaving mirror. So the best for shaving mirror, concave mirror. Then for car headlamps, searchlight, spotlight, and the likes, we use a parabolic mirror because it gives us a parallel beam of constant intensity. Then lastly, for convex mirror, they are used as driving mirror because they have a wide field of view and they always give us erect image. Just that objects are closer than they appear as the image on the mirror. Now let's move to mirror formula, where we are going to give the connection between the focal length f, between the object distance u, and between the image distance v, and we connect it to magnification, which is v over u. Now let us consider these two converging mirror. So for this first one, the object is placed between the principal focus and a center of curvature. So what we have here is the object, this is the image that will be formed. So the image is really inverted and magnified. For this one, it is formed at the back. So it is virtual, erect, and also magnified. So the mirror formula actually relates the object distance from this point, this is the object, and to the pole. This is what we call the object distance u. So this is the image, this is the pole. So this is the what? Image distance v. The distance between the principal focus and the pole is called focal length. And we can prove from here that 1 over f equals to 1 over u plus 1 over v. This is what we call the mirror formula. The connection between principal focus, the object distance u, and the image distance v. Then we also have what we call the magnification. So the magnification m is how big, or what is the change in size. For example, the image is longer or is bigger than the object here, so it is magnified. So in this case, our m becomes what? V over u. And we've shown in our previous lessons that this same thing as what? Image height over object height. So meaning this v over u is same thing as what? Hi over what? Ho. That's another point. Then another thing they can ask you to get is distance between the object and the image. This is the object in this case, this is the image in this case. So the distance between them, let's call it d. Obviously, u plus d will give us v. So in this case, the distance equals to v minus u. This only works if the image is real. If the image is real, what happens? They will be on the same side. But unlike this is the pole. So this is u, object distance. This is v, image distance. So distance between the image and the object, in this case d in this case actually equals to what? V plus u. So for virtual image, whenever a mirror forms a virtual image, the distance between the object and the image is the addition. But if it's, real image, is going to what? Difference. Although it is not always v minus u. Sometimes u can be more than v. In this case, the object is here. If the object is somewhere here, the image will be somewhere here. So it is either what? V minus u or u minus v. So in that case, we'll put this sign here. The absolute value. In case if u is small, you get negative. So absolute means neglect the sign. Neglect negative sign. So this time between what? Then note this extra point. Note this. For a converging mirror, the focal length is always positive. Always positive. That's first point. Then the image distance is most times positive, meaning the image is formed at the front in this case, except for this case when the object is between the pole and the principal focus, where it's going to be formed at the back. Anytime you have a virtual image, or let me just remove this, you generalize it. Then for a diverging mirror, note, converging mirror is also known as what? Concave. Concave mirror is converging. Then for a diverging mirror, f is less than 0, negative. Without being told, in any question we are given, just note for a diverging or for a convex mirror, focal length is negative. Why? The focal length or the center of curvature is at the back of the mirror. We've explained this in our previous class. So for converging, f is minus, f is plus, diverging f is minus. Then for a virtual image, Anytime a virtual image is formed, it implies that what? V is going to be what? Negative. The image distance will be negative. Whenever the image is virtual, is formed at the back, that distance is taken to what? To be minus, not plus. Note that. And magnification will also be minus, because m equals to v over u. But in short, for virtual image, v is minus. For converging mirror, f is plus. For diverging, f is minus. And this is what? The mirror formula. Although, to save time, we can add two extra formula for magnification. Sometimes you will not be given u and v together. You can give us f and v in terms of m. So we can further get other formulas for magnification in addition to this, which we will note here. Our m can also be equals to, for example, if you are not given v, we can write this v in terms of f and u. If we make v the subject here in terms of f and u, I will substitute here, we are going to get the magnification equals to what? U minus f over f. If we make u the subject in terms of v and f and we impute here, we'll get magnification equals to what? V minus what? Zf minus 1. So this extra formula for magnification, f u minus f. This in terms of f and u. If the question is not talking about, the image distance, and when it's not talking about object, then we use this. But this formula is not necessary. So if you're not using this formula, you have to solve simultaneous equation. You solve simultaneously. If you are given m and v, not u, and with this formula. So this is what you need to know about mirror formula. Now let's solve questions on reflection of sound in general. Okay, before we solve question, record. Sometimes instead of giving you a focal length, they might give you the radius of curvature. You should also know that focal length is half of the radius of curvature. Anytime you are given radius of curvature, divide by 2 to get the focal length. What we need is the focal length, not radius of curvature. So we're solving question on curved mirrors, reflection, under reflection. So first question is from 1978, number 45. What's the question?
Which of the following is true for the image formed by a convex mirror?
Which of the following is true for the image is formed by a convex mirror? You have to note from our lecture, we've already established that for a convex mirror or a diverging mirror, the images formed are always virtual, erect, and diminished. And the focal length of convex lens are always negative. Now, what's the question?
The image is always virtual.
Yes, always virtual, correct. I.
The image is always erect.
Always erect, correct. I.
The image is never magnified.
Yes, never magnified, it's always diminished, correct.
The focal length is negative.
Focal length is negative, yeah, that's also correct. So it means option I to IV is correct. That's the option D. Option D has 1 to V being correct. 1979, number 16, the question.
An object is placed 30 cm from a concave mirror.
That's U.
Of focal length 15 cm.
15 centimeters.
The linear magnification of the image produced is?
We are looking for M. Recall the shortcut formula during, when I was doing lecture for the mirror formula. Their magnification is also equals to F. This will make your calculation to be quick. F is 15, 30 minus 15. So that's 15 or 15, M is 1. So it means the object is placed at the center of curvature. So that's where we have all the same size. So that's the answer straight. But if you have to use the normal formula, magnification is V over U. We know U, but we don't know V. So you have to go for V first. Using the mirror formula, 1 over V equals to 1 over U plus 1 over what? V. F is 15. U is 30. From here, 1 over 15 minus 1 over 30 equals to 1 over V. The LCM is 30. 15 here, 2 times 1, 1. So that's what? 1 over 30 equals 1 over V. From here, it means V is what? 30. Then now come back and write M equals to V over U. m equals to 30 over 30, m equals to, so to avoid this, you can use it straight. But always put the correct units for the focal length. Next question. Now, 979 about 32.
Yes.
The question.
A concave lens of focal length
A concave lens of focal length
20 centimeters
20 centimeters
forms an image half the size of the object.
forms an image half the size of the object. It means the magnification is half. Continue.
The object distance is
We are looking for object distance. Similar to what we just did now. Magnification in terms of f and u is what? F over u minus f. So 1 over 2 equals to 20 over what? U minus 20. So multiply u minus 20 equals to 40. U is 40 plus 20, u is what? 60. 1981, question 12.
which of the following statements is applicable to a real image formed
Which
by
of the following statement is applicable to a real image formed by
a concave mirror?
a concave? Before we continue, for a concave mirror, the images formed are always real and inverted, real and inverted, real and inverted, except when the object is placed between the principal focus and the pole, where it is virtual and at first it is behind T, behind the center of curvature, it is what? Diminished. At the center of curvature, it has same size. Between center of curvature and principal focus, it is magnified. Between principal focus, on principal focus itself, the image will form at infinity. Then, when we move it closer to the pole, it's magnified. Now let's continue.
I.
I.
It can be observed on a screen.
It can be observed on a screen, meaning the image is always what? Virtual. Sorry, always what? Real. They are always real, but we have exemption. So we cannot take it. It's not always. Most times yes, but not always.
2. It is always inverted,
It's always inverted,
being observed
except
on
where?
a screen.
Being observed on a screen. Okay, that is correct. If you can observe it on a screen, then it will have to be inverted. Meaning when it's real. When we are told that it is observed in a screen or on a screen, it means it is what? Real. And anytime the image is real, it is what? Inverted. So I is wrong, I is correct. Why is I wrong? Because they said it's always what? Real. It's not always real. Sometimes it can be what? Virtual. But let's take question again from beginning.
Which of the following statements is applicable to a real image
Okay, to a real image.
formed by a concave mirror?
So since some of the question, we are particular about real image. So meaning we have no business with this last part. All our focus will be here. So first, option A say I says what?
He says it can be observed on a screen.
All real image can be caught on a screen. So I is correct if it's real image. I.
It is always inverted, being observed on a screen.
Yes, always inverted. All real are inverted. I.
It only seems to exist.
It always.
It only seems to exist.
It only seems to exist.
That means it's not real, but it only seems to exist.
If something only seems to exist, it means it doesn't exist, but it seems to exist. Does that mean it's virtual? Let's keep that option.
IV. It is formed by the actual converging of rays of light.
Yes, all real images are formed with what? Real rays. It is only virtual rays are formed with what? Extrapolated rays. So this is also correct. Is that all the options?
Yes, sir.
What's A?
A is I, and I only.
I. This must be part. A is wrong. B.
I, and IV only.
I, and IV only. Obviously, yes.
C, I, and I only.
No, I must be there.
D, I only.
No. So the answer is what? I, and IV. Option B. Let's move to the next question. 1982, question 7. What's the question?
In order to produce a parallel beam of light,
In order to produce a parallel beam of light,
a lamp is placed at a distance from the concave mirror
a
equal to
lamp
that.
is placed at a distance from the
Concave mirror equal to that.
concave mirror equals to this concave mirror. This center of curvature, this center of focus is the pole. For us to get parallel rays, it means the light must pass through the principal focus. Because any ray that passes through principal focus is reflected what? Parallel to the principal axis. So we can only get parallel rays when the lamp is placed at the principal focus. Now let's go to the option.
A. At the radius of curvature.
No, the radius of curvature is C. That's wrong.
B. Half the radius of curvature.
That's correct, because from here to here is focal length, and focal length is what? Half the radius of what? Curvature. So the answer is B. What option C first?
C. Half the focal length.
No, half focal length. If you place it here, we are not going to get parallel rays. Next.
Twice the focal length.
So the focal length is here. Wrong. The answer is what? Half the radius of curvature. 84, question 6.
For a concave mirror to form a real diminished image.
For a concave mirror to form a real diminished image, that's RID. Read.
The object must be placed.
Let's, without checking the option, recall. For a concave mirror, just find a way to memorize this. We have what? Read, ris, rim, infinity, and we have position. Position of object and image. So let's be U, this one will be V. So we get read when the object is placed what? Behind the what? Center of curvature. Behind center of curvature. We get ris if it's on the center of curvature. We get rim in between what? Center of curvature and the focal length. Here it is on the focal length. Here between focal length and what? Pole. So to get real inverted diminish, it must be behind the center of curvature. If this is C, the option placed behind. Now option.
The options. A. Behind the mirror.
No, behind the mirror, you cannot place object behind the mirror. It's not form anything because the mirror is coated. When you place an object behind the mirror, you not form any image. It must always be in front. So that cannot be the answer. B.
Between the mirror and in focus.
And in focus, that's between P and F. No, that will give us verb.
C. Between the focus and the center of curvature.
That's between F and C. We get rim, not read.
D. At the center of curvature.
If you put the center of curvature, it will be ris, not read.
E. At a distance greater than the radius of curvature.
Yeah, this radius of curvature. Distance greater meaning behind it. So the answer is what? D. A distance beyond what? Radius of curvature. 1984, question 30.
The image and object distances.
The image and object distances
of a converging mirror.
Are
related by the equation.
1
over F is equals to 1 over V plus 1 over U. And the magnification of the image is M is equals to V over U. Which of the graphs below represents the relation between M and V?
Between M and V. Then if you have to plot the graph of M to V, what will it give us? When you look at this directly, we can see that M and V, they are what? Directly proportional. And it has no intercept. Ordinarily, mainly looking at this, you want to draw a graph like this. But this is going to be wrong. Why? Because this U is not fixed. Because if U is fixed, V and M also be fixed. So meaning, if V is changing, U too will change. So in that case, we have to include, the focus. What's actually constant here? V changes, U changes, M changes. It is only F that do not change. So to sketch the graph, that constant must come in rather. So since we have only M and V, we have to eliminate U. We need to eliminate U away. And if we eliminate U, recall the formula we gave, we are going to have M equals what? V over F minus 1. It's part of the one I gave you. So we can also write it as, M equals to 1 over F times V minus 1. Y equals to mx plus c. Meaning if you sketch y, this y-axis. Y-axis represents magnification, x-axis represents v. Then the slope is 1 by f. Since f is constant for a particular mirror, we can now apply this. This minus 1, this seems intercept where it cuts y-axis. So it means we are going to sketch a straight line graph that will cut y-axis at minus 1. So suppose this minus 1. From this minus 1 here, we'll get a straight line graph. So this is the kind of graph you are going to get. And the slope here is what? Reciprocal of the focal length. So when you check the graph, which of the option has this graph?
C.
Option C. That's the correct answer. 1985, question 30.
An object is placed 15 centimeter in front of a concave mirror of radius 40 centimeter.
All we need is F not R. Since R is going to be 40, our F is 40 over 2. So it means we are given focal length to be 20 centimeters.
The image formed is.
The image form is. First, let's look for, first look at this. The image is behind or is between F and C actually. But let's look for V. And we can even look for the M. If we know the magnification, we can guess where the object is placed. So our M equals to F over what? So M equals what's F? 20 over 15. Sorry, over 20 minus 15. Okay, 15 minus what? 20. Is there a mistake in the formula? Alright, no mistake. So for me, M becomes 20 over what? Minus 5. So M equals to minus 4. It means the image is 4 times bigger than the object. If this is the object, D is the image. So we are getting what? A magnified image. This minus shows that the image is somewhere at the back. So we are having a virtual and magnified image. That's them. Now let's check the option. Option A.
Option A. It is virtual and 60 centimeter behind the mirror.
60 centimeter behind. No. Now they are talking about the image distance than V. We cannot get V. So M is V over U. What is M here? Minus 4 equals to V over what was U? 15. So V is what? Minus 60. The minus means at the back. So it is 60 centimeter behind, not 15.
Yes, 60 centimeters behind the mirror.
And it's virtual, Abi?
Yes.
That's the answer. A.
Virtual and 60 centimeters.
Virtual and 6 centimeter behind. Option B.
Real and 60 centimeters.
It's not real, it is virtual.
C. Virtual and at infinity.
Not at infinity.
D. Real and at infinity.
It's never real. So the answer is A. Virtual and form 6 centimeter behind, 6 centimeter behind the mirror. 1985 question 32.
A convex mirror is used as a driving mirror.
It's used as a driving mirror. 1985 question 32. Okay.
A convex mirror
A convex mirror
is used as a driving mirror.
is used as a driving mirror
Because
what is I?
its image is erect.
Its image is erect. Yes.
It has
Because for a convex mirror, we always have what? VE. Always erect.
It has a large field of view.
Yes, it has a large field because of what? Its diminishing port ability. So it has a what? A large field of view.
I. It has a long focal length.
It has a long focal length. That doesn't matter. It doesn't matter. A concave mirror can also have a long focal length. That's all. So that's why it's I. Option what?
Option D.
Option D is I and I. D is the correct option. Okay, B.